Hi, everyone. Welcome. I'm Tyler from the Cove team, and we're here today with two very special guests. We have Dr. Charlie Conway, who has a PhD in neuroscience and is not only the chief scientific officer at Biohaven, but he was also the lead biologist on the team of scientists that identified new CGRP blockers, which he'll give us more background on today. We're also joined by Dr. Sarah Crystal, who is a neurologist at the New York Headache Center, as well as Cove's medical director and a migraine sufferer herself. Thank you both for being here today. Today,
Thanks, Tyler.
Of course. Today, Dr. Conway will be sharing with us what CGRP blockers are, how they work, why they're helpful for migraine sufferers, and the story of how he helped discover new ones. He'll also be answering your questions, whether you submitted them last week or you're sharing them in the comments here today. Before we jump in, I want to remind everyone again that we cannot give any personal migraine diagnoses or answer any questions about your personal migraine history during this live event. If you are looking to speak to a doctor virtually, we can help with cove.com. And before we start, I want to say thank you to everyone who messaged us questions ahead of time. We were so excited to see so many come in. And with that, I think we're ready to start. So I'll hand it over to you, Dr. Crystal.
Thank you. Dr. Conway, I'm so excited to be speaking with you about the CGRP blockers today. We know how debilitating migraine can be, and I'm thankful to you for your role in helping bring relief to so many patients suffering with this condition. I myself have treated many patients who describe these medications as life-changing. With that, I'd like to dive in. Can you tell us about how you became interested in pain and headache medicine?
Sure. Thank you, Dr. Crystal. It's really a pleasure to have a chance to meet someone who not only works with people who have that disease state, but understands from personal experience how devastating and debilitating that can be. So I was interested in learning about the brain, and particularly in brain development. And so in graduate school, my dissertation research was focused on how pain changes as the brain develops. And it turns out that adults have advanced mechanisms that help inhibit pain signaling that newborns don't have. Specifically, adults have local inhibitory circuits and descending pathways from brain to spinal cord that reduce pain. And this develops top to bottom, that is from brain towards the spinal cord. So my dissertation research characterized that paradigm. And so, getting a PhD means you're specializing in something, kind of like physicians specialize in certain areas. And so my specialty became pain, and I carried that focus with me into pharmaceutical research, looking at the big problems that need more attention, like migraine.
Thanks. So for those of us who may not be familiar, can you describe what CGRP is and how it contributes to migraine?
Sure, I'm happy to do that. I brought some slides and a little video clip. So Tyler, if you'll put those slides up, we can kind of walk through that. So first of all, what you want to step back and understand is that when nerve cells communicate, they release chemicals. So when you have a sending neuron sending a signal here on the left and a receiving neuron on the right, the actual cells don't touch. There's a gap between the cells, and that gap is called a synapse. And so when a sending neuron sends a chemical, there's two types of chemicals it can release. One is called a neurotransmitter that either activates or inhibits the receiving neuron, and another is called a neuromodulator that modifies the cell's response to input. And what we're going to talk about next is we're going to zoom in right to that space in the synapse. And so let's go to the next slide. So here on the top, you have the trigeminal nerve. You can see that CGRP are containing little vesicles in that nerve. And then on the bottom is the receiving neuron. So calcitonin G-related peptide is a chemical, a neurochemical that's released by the trigeminal nerve during migraine. And this neuropeptide floats across the gap of the synapse and it binds to the CGRP receptor on the receiving neuron. Next slide, please. We're going to zoom in right now to that receptor. And so here you see the CGRP molecule shown in dark red, and then the CGRP receptor shown in purple. And the way this works is that CGRP binds to the receptor like a key opening a lock. And when that lock is open, it changes the brain's response to input. And so it's a neuromodulator. And this leads to hyperexcitable abnormal brain signaling and the constellation of symptoms that you see here. But I think it'll be helpful to watch this little 30-second video clip, and that may help give you some visual idea of how it works.
Migraine is a disabling disease caused by trigeminal nerve overactivity. During migraine attacks, a brain chemical called calcitonin gene-related peptide, or CGRP, is released by the trigeminal nerve. and changes the brain's response to input. When the trigeminal nerve is activated, CGRP is released both in the brain and outside the brain. CGRP then binds to receptors and causes problems in brain signaling that lead to disabling symptoms which disrupt normal daily activities.
So that really is the key, is that this sequence of events, it really is disruptive to normal activities. So at baseline, CGRP is not usually being released. However, when we measure plasma levels of CGRP in people who don't get migraine compared to people who do get migraine, it seems that people who do get migraine have some ongoing activation of the trigeminal system because the CGRP levels are 3 to 5 times higher in people who are susceptible to migraine versus those who are not. So it seems like they're always closer to the threshold of being thrown over into this hyperexcitable state that we call a migraine attack.
So that's a great explanation. Can you now explain how the CGRP blockers actually work to reduce pain and the other symptoms of migraine?
Sure. So I brought along another little set of slides and a video clip from our website. So let's start with that. So there's really 2 different ways that CGRP blockers work. On the left, you can block the CGRP receptor. So when a CGRP oral receptor antagonist, a GPANT, or an injectable CGRP receptor antibody called a CGRP mAb binds to the receptor, it's like putting tape over the keyhole. It means that the key can't get in anymore, and it blocks out the receptor so it can't unlock the lock. And so that's how one way that CGRP blockers can work. Over on the right is another way that CGRP blockers can work, and this is by blocking the CGRP neuropeptide itself. So when an injectable CGRP antibody, CGRP mAb, is bound to the receptor, is bound to the CGRP peptide itself, then that key isn't free to find its way into the keyhole and unlock the lock. So it's like a magnet. If a key is attached to the magnet, it can't fit into a hole. And so CGRP antibodies, when they are circulating in this space, they actually suck up the key in that gap before it can get to the receptor on the other side. And that means that when it's connected to the antibody, then it can't find its way to the receptor. So those are kind of the 2 different ways that CGRP blockers work. And now maybe if we play a little video, we can kind of talk about the consequence of that.
Together, these effects lead to overactive abnormal brain signals, which cause multiple symptoms, including severe headache pain. Many patients with migraine also report being oversensitive to light and sound. Patients often experience nausea or vomiting, which can be severe. Other symptoms of migraine include overactive senses of smell and taste, visual problems called aura, and skin hypersensitivity called allodynia, where normal activities like brushing hair are painful. With this overwhelming set of symptoms lasting 4 to 72 hours, migraine is one of the leading causes of disability worldwide, affecting nearly 1 in 7 people. Migraine is 3 times as frequent in women as in men, and strikes more often between the ages of 15 and 49 years old. Most patients with migraine cannot work or function normally during an attack.
So clearly from this description, if you don't know somebody who gets migraine, the migraine is not just a bad headache. It's a real disabling neurologic brain disease. And really, it has the kind of disability that people just check out from their lives. And so they miss important events, they miss work, they miss activities. It really is disruptive. And what's mostly disruptive about it is it's so unpredictable. You have no idea when it's coming on. So that's just one of the situations here.
Yeah, many patients describe not just fear of an attack itself, but not being able to plan their lives because they're worried about an attack. So Dr. Conway, you led one of the first drug discovery teams to identify a CGRP blocker. How did you come to focus on the CGRP molecule?
Sure. Well, so actually, my work in this area started 20 years ago, back in 2000. And we were following the science of some early researchers. So Lars Ebbinson and Peter Goadsby, along with others, had pointed to a role for calcitonin gene-related peptide in migraine. And here's just some of their seminal research. And so as a PhD, you're reading scientific articles all the time and you're following the science. So in 1988, they showed that CGRP levels were increased when you stimulated the trigeminal nerve in humans. In 1990, they showed that those levels were increased during headache in humans. And then in 1993, they showed that those levels dropped coincident with headache relief following treatment with a triptan or with dihydroergotamine. So this was really the key science that led to this space. And actually, if we go to the next slide, these two scientists and two others, Mike Moskowitz and Jess Olesen, just earlier this month, received the top brain prize. It's the Lundbeck Brain Prize awarded by the Lundbeck Foundation, a Danish company. And Mike Moskowitz was the first person to suggest that the trigeminal nerve was releasing something. Lars Ebbinson and Peter Goadsby were the ones I just showed you, described how that worked. And then Jess Olesen did a clinical trial where he infused CGRP in human patients and showed that it could produce an attack. And he was also the lead on the first clinical trial of a small molecule CGRP receptor antagonist, which we now know as the GPANs.
Can you describe the process from getting from a molecule to a marketed product that we can prescribe to patients?
Sure, it's really, it's an iterative process. So I like to show it kind of as a funnel. And what you do is you start with an idea, and the idea is a scientific idea that we just talked about of you want something that can interrupt how CGRP connects to the receptor, right? And so the way that this happens in drug discovery is you design an experiment that can show when a molecule has an action of blocking CGRP connecting to the receptor. So for us, that's a CGRP receptor antagonist assay. And the way this starts is you run what's called a DEX screen. Now that's like pharma lingo, so let me just explain what that means. Every time a chemist makes a molecule, he sets aside a little bit of what he makes into what's called a compound library. And that compound library becomes known as the company's deck. So that's a deck of every single molecule that the company's ever made. So when you have a scientific idea like a CGRP receptor antagonist, what you do is you run an experiment where you test every molecule in your deck against that scientific question to see if there are any molecules that have a signal. And those are called leads. And then the leads are never good. They have a little bit of what you want, but they have a whole lot of what you don't want. And so they may have like off-target activity at cardiovascular ion channels, or they might cause drug-drug interactions, or they may not be absorbed easily in the body. So you have to go through all these iterations. What's happening is chemists are making brand new molecules that have never been made before. And biologists are testing those molecules in assays to show the chemists what happens between the change that they made and the readouts that we have. And so drug discovery is really a partnership between chemistry and biology. And I had the good fortune to be paired with a really stellar, brilliant chemist, Jean Debochik, who led the program with me. We were program co-chairs. That process of changing molecules and finding out what works and what doesn't, it actually can take 10 to 20 years and cost $1 to $2 billion. So that's a typical, profile of what it takes to do things. You're constantly changing the molecule. You're finding the properties that it wants. You're optimizing it for humans. And then you go into clinical trials, which takes several years. And then you hope to be one of those few drugs that actually makes it through what I call this drug discovery gauntlet and becomes an approved drug. And I have so many colleagues and friends who are just as dedicated as I am, and they work their whole lives like I have, and never have seen a drug get to the light of day. So I'm one of the lucky few that is able to bring something forward and see the results. And I can't tell you, what's so heartwarming to me is when I get a letter or a note from a patient talking about how they've benefited from getting a new treatment.
Can you tell us a little bit more about leading the research team? Like, did you realize at the time you were working on it the magnitude of what this would become?
So, you always hope that it's going to have fruition and that it's going to, have a positive benefit. You never know. And there's also things happening that you don't control. Like, the company you work for may decide to stay in the area, or maybe they decide to mix things up and get out of the area. So that's actually what happened to me. So the company I was working for decided to exit neuroscience and to out-license the assets. And so I was part of the out-licensing team. And so in sharing the results and the data with the board of directors of Biohaven, they liked what they saw, they acquired the asset, and then I had the good fortune to join the Biohaven team and continue the work and follow it not just from the bench, but into the clinic and into becoming a marketed drug.
Can you tell us about what the CGRP treatment landscape looks like today?
Sure. So I think I brought along a slide for that, Tyler. There's currently 6 different CGRP blockers. Now, as we talked about before, they can work by different ways. So 3 of these block the receptor and 3 of them block the CGRP neuropeptide. So let's look on the left. So the 3 that block the CGRP receptor, there are 2 oral CGRP receptor antagonists called GPANTs, which are for acute treatment. What that means is they met the FDA requirement of efficacy at 2 hours to abort an attack when it's coming on. And that means that they were significantly different from placebo on pain and the patient's most bothersome symptom. And by most bothersome symptom, it's defined as either nausea or hypersensitivity to light or sound, which is called photophobia and phonophobia. Then another agent in this CGRP receptor blocker class is an injectable CGRP monoclonal antibody that blocks the receptor. This actually is a preventive treatment. Instead of taking it when an attack comes on, you take it beforehand on a regular basis. And in this case, what's measured for FDA approval is reduction in the number of headache attacks over a 3-month period. And so this treatment would have met the FDA's requirement. Then on the right, there are 3 more CGRP monoclonal antibodies, but these actually bind to the peptide itself instead of the receptor. This is like a magnet with the key. And so these 3 are also designed and approved for the preventive treatment of migraine, which means they reduce the number of attacks or the severity of attacks. I will point out there at the bottom of the slide, though, these things are very different size. So take a look at this. So a GPANT is something called a small molecule. And we call it a small molecule because really it's pretty small. So the way you measure molecule sizes is something called molecular weight. So GPANTs are around 500, 600 molecular weight. Just so you know, their CGRP is about 6-7 times larger. Its molecular weight is 3,700. But look at the CGRP mAbs. They're like almost 300 times bigger than the GPANTs, around 145,000 molecular weights. And so these molecules have different properties. And I just wanted to share with the group what the advantages of different things are. Antibodies tend to stay in your body for a long period of time. By a long period of time, I mean, a half-life of a month. So it just takes 5 half-lives for a drug to clear your body. So you might take an antibody and get, weeks and weeks of benefit. In contrast, a GPANT, an oral small molecule, usually has hours of benefit, 10 to 12 hours, something like that, in which case you might get benefit for a couple-day period when you're trying to abort an acute attack. So there's just some of the differences between the 6 CGRP blockers.
That's a great overview. Thank you. Can you tell us about where you think migraine treatment research is heading?
Sure. So look, migraine researchers, they're looking at the current landscape. They're trying to understand what's good and bad about the things that are out there today. And every generation of scientists is trying to bring forward something that has an improvement. And that might be an improvement in efficacy, or it might be an improvement in tolerability, or in best of all worlds, it might be an improvement in both. And so I think, for those folks who don't know, these anti-CGRPs are some of the first molecules ever that were specifically designed to treat migraine. Most of the previous drugs in this area were borrowed from other disease states to treat migraine because they worked against the hyperexcitable neurons. Like some of the drugs were borrowed from epilepsy treatments, etc. So every generation is trying to make a better molecule that has some advantages in some ways. So now, for the first time, we're able to identify CGRP as a key mediator of migraine, and now we have multiple keys that we can, use to treatments to go after those disease states. So I think what's important is the science is continuing to evolve, and as it evolves, we may find more answers to our questions. For example, we know that CGRP is released during a migraine attack. What we don't really understand is what's the key triggering event to that attack. And understanding that may lead us down a road to new treatments. It also could be that there are different relative responders. And so there's other areas that we could go after scientifically in the future. So I think it's the anti-CGRPs are an advancement, and we continue to hope that we can bring new advancements forward in the future.
Can you talk a little bit generally about patient diagnosis and treatment trends in migraine?
Sure. Yeah, actually, there were two really nice epidemiological studies. I brought along a slide, Tyler, for that so that we can take a look at that. So this first study was conducted by Richard Lipton and a team, and they interviewed around 700 patients who had a history of less than 15 headache days per month. And for those of you who don't know, according to the International Classification of Headache Disorders, that would fall into the episodic migraine category, which is a funny name because it's a made-up term. It's not a diagnosis. The only real diagnosis is migraine with and without aura. So they would follow into a category where people would need acute migraine treatment. And so these patients, if you look down the left, it shows you what percentage of these patients actually talk to their physician. And this was surprising to me. Look at this, 45% talked to their physician and 55% didn't even talk to a physician, even though they were having a regular headache days per month. Now let's keep following down the left. Of those 45%, a subgroup, only 39.5% left, were diagnosed. And then a subgroup of that, 26.3%, were actually treated. So only about a quarter of patients who consult their physician and get diagnosed are actually treated. And these are for the acute treatment of migraine. So that's the patient journey for people who need acute treatments. Let's look at the next slide. This now is patients with greater than 15 headache days per month, and that's part of the diagnosis of chronic migraine. Here, it's similar, only about 40% of patients asking the physician for help, which is shocking, right? Because you've got more than 15 headache days per month, and you're not asking your doctor for help. 10% of those result in diagnosis, and less than 5% are diagnosed and treated after receiving consultation. So what that says to me is people don't realize that what they're experiencing is not normal and not okay, and they shouldn't just accept it. I think it gives us an opportunity here to talk about the idea of bringing forward different concepts of not being afraid to bring up to your doctor the experience that you're having and talk about it.
Yeah, I think that's very true. I know I tend to see, as a headache specialist, I tend to see the majority of patients I tend to see have chronic migraine, and some of them, yeah, again, have never seen a physician before. But I wonder, I don't think my population is necessarily representative of the general population, and I'm wondering, what is the typical migraine frequency in the general population?
Yeah, so actually you might be surprised. And it's funny because I talk to a lot of specialists and they're like you, they see kind of the worst of the worst. Here was a really large study conducted by Andy Blumenfeld. 8,000 patients. On the x-axis is showing the number of headache days per month in different bins. On the y-axis is the percentage of patients that fall in the different bins. And look, the vast majority of patients, the most frequent, is having 2 to 3 attacks. So about 2/3 of patients are having 6 or fewer headache days per month. On the far right is the diagnosis for chronic migraine, and it's only about 5% of patients are in that diagnosis, and then there's groups in between. The good thing, though, is that now we have anti-CGRPs that work in both populations. So I think there's some hope here and there's some good news for patients across the spectrum.
So we're getting some questions from the audience. One question that just came in, I think for you, Dr. Conway, is why does CGRP blockers work for only some people and not for others?
Yeah, that's a great question. So when we look at clinical trials and the history of clinical trials, it's usually about 2/3 of the patients that respond in the acute treatment of migraine to this new class. And part of that, we think, is just that not everybody has the same underlying cause of their migraine attacks. And so what's good is we've actually figured out that for a good majority of patients, there's a CGRP mechanism that's underlying their attack. And so it's informative to both the patient and the physician when we have a positive result from that, because then they understand what to use. And it's also informative when there's a negative result, because then they can go on to try different approaches. So we really think that there's a diversity in the underlying causes. And that just brings to light what we talked about before with Dr. Crystal, is there's still more science to understand here. And maybe there's another molecule like CGRP that's also involved.
Great. Another question we just got is, has the relationship between CGRP levels and menopause been studied?
Do you want to start with that, Dr. Crystal?
I am not aware of studies on CGRP levels and menopause.
Yeah. So what I said in general is that patients who have migraine tend to have higher levels of CGRP all the time. But there's this relationship between CGRP and estrogen. And we understand this because of two basic things. One, the highest frequency of migraine attack occurs between 15 and 49 years old. So what's happening at 15 is sexual maturation and the release of hormones. And so estrogen is one of them. So it looks like there's a relationship between estrogen and CGRP that is causing an increase in migraine frequency. And so also then postmenopausal, often, it's not always the case, but often there's a reduction in the number of attacks. And so I don't know what the epidemiology is in terms of understanding the big picture to that question, but I think those concepts that I just shared are kind of the underlying relationship between the two.
Got it. Another question that just came in is it safe or appropriate for patients to take CGRPs along with other migraine treatments that are currently on the market?
So the anti-CGRPs as a general class have a pretty good tolerability profile. And so I think that kind of question, is it safe, is really a question for a patient to talk to their physician about. I think, it may be that part of the question is about, can you take an anti-CGRP and a Japan at the same time? And it's early days in this situation. There's been a handful of publications and a handful of patients studied there. So I think really that question is more of a medical question, best addressed to having a conversation with your personal physician.
Great. Thank you so much. So, I think we're actually at time. So, just want to wrap things up. Remember that you can always visit us at withcove.com to connect with a doctor for help with your migraine and for content on our blog about all migraine related topics. We hope this was helpful and educational for you. And if you missed any of this, you can check this out on our social channels later today. Before we go, I want to say a big thank you to Dr. Conway and Dr. Crystal for taking the time to join us today to answer these great questions. And also thank you to everyone who shared their questions and tuned in with us. And if you have any other questions, you can find more on withcove.com on our blog, or feel free to reach out to us directly through DMs. Bye, everyone. Take care.
Thank you.
Bye-bye. Thanks, everybody.